Okay, so today we'll be looking at the prerequisites for the stability and frequency response analysis, or basically the stability analysis. Clear? So my objective for this particular class and for the next coming class would be two things. One is to study the timing behavior. Okay, so the first objective talks about the timing behavior of a first order and a second order LTI system. Okay, so what is this LTI? Yeah, so it's a linear time invariant system, and we are going to discuss about this with respect to the system poles. Okay, the study is basically with respect to the system poles and zeros. Okay, so in order to study the timing behavior, I'm going to look at the system poles and zeros. This is accomplished by making use of what is known as S-plane. Okay, so I'll be using this S-plane and trying to talk about the locations of the poles and zeros of the system, and then I will try to evaluate the behavior or the timing behavior of my system. Okay, so that is the first objective, and in the second objective would be to study the frequency. So now in this case, again I am going to use those system poles as well as zeros, but what I am going to do is, like, rather than using an S-plane, I am going to use a Bode plot. Okay, so in this case I will be using a Bode plot, and these are prerequisite for our stability analysis. Okay, so until otherwise we understand these two topics, it becomes difficult for us to really to know how to control the unstable system. Okay, so that's the reason why I'll be spending this class and probably the Friday's class with these two, addressing these two topics. Clear? Yeah. So now in the process of doing this frequency response, we will also talk about the Bode plot. I guess you people have not read about this Bode plot in your control systems, right? You have studied? Okay. So then what I do is, like, I'll just make a quick revision of what it is. Okay. So about the Bode plot, and then we will also talk about the frequency response, a small introduction about the frequency response, and then later we'll see like how these poles and zeros are actually changes the frequency response. Okay. So as a first topic, the time response. Okay, so under this time response, what I'm going to do or what I'm going to study is the step response. Okay, so we know that the step response of an LTI system has two components, right? So the very first component is nothing but the transient, or it can also be called as a natural response. Yeah, and the second component is nothing but the steady state or forced response. Okay, so this we have already studied, like the time response for a step input will have two components. One is the natural response, the other one is the forced response, but I just want to emphasize for the first order as well as for the second order. Probably we didn't have studied about the second order system till now. What we do is, like, we will apply the same concept onto the second order system and see what makes this second order system to either oscillate or to have over damped or under damped. So such cases we will be studying in this particular class. Okay, so this is as far as the time response is concerned. Now what happens the moment I go into a frequency response? What is the type of input? So in this case, the type of input that I am dealing, it would be a step input, right? So in the case of a frequency response, what type of input I will be using to analyze my system? For timing behavior, I use a step input. Yeah, sine. Yeah. So basically what we will have here is a sinusoidal function. Okay, so we will be using this kind of input to analyze an LTI system when we talk about a frequency response, where we try to vary the frequency of this particular sinusoidal input and then talk about the response of my, or the frequency response of my system. Okay, now this is the thing that I want to prove, that when I look here, the transient part is basically happens just because of the system poles. Okay, this is the proof that I want to make it. Okay, so basically the system poles is the one that is responsible for the natural response or the transient response. Okay, so my main point here is to make sure that you are understanding this particular concept. How do I modify the behavior of my response is by working with the poles. Okay, and again, when I talk about a pole, it's the system pole that we are talking. Okay, now you might have a question like, do we have any other poles apart from this? Obviously, we will have some poles. I will talk about that pole as well. Okay, so as of now, this is the overview, and I just want to talk about the first part, that is the time response. Okay, and let me take a step response for a first order system. So let me take a general case where I have a first order system having a single pole in it. Okay, so I have something like a divided by s plus a is the transfer function which I labeled as h of s of my system. Okay, now to this, the input and the output signals are x of s and y of s, and now that to this system I just want to apply a step input. Okay, now let me draw the step input with respect to the time. So let me have it at around time t equal to 0. I have a step input like something like this. Now how do I represent this in terms of this x of s, the step input? 1 by s, right? So this is nothing but 1 by s. So now that I just want to evaluate this y of s, so what do you do in order to evaluate that? Just multiply? Yeah. So the basic simple formula is something like you multiply both the quantities x of s with the h of s, and you know that you end up having something like a divided by s into s plus a. Okay. So now I also, before I really start talking about the final output, which in terms of time, okay, so before I try to derive this y of t, I also want to talk about the poles, how it exactly lands in my s plane. Okay, so let me have this s plane, j omega and sigma is nothing but the real term, and the j omega term is nothing but the imaginary. So basically the s is defined as something like sigma plus or minus j omega, right? So any kind of pole could have something like sigma plus or minus j omega, right? So now how do I place my pole that I have it in my transfer function h of s? Yeah, minus a. So now is this pole is a real or an imaginary or a complex? It's a real, right? Yeah. So since I have it as a minus a is the pole location, right? So this is where the pole comes from. Now how do I evaluate that? Is nothing but take this particular term, which is the denominator polynomial, and equate it to 0, which is nothing but the characteristic equation, and from there I can get this particular quantity, right? Yeah. So now in this case, what happens is there is no imaginary part or the imaginary component that is available here. Okay, so the only term that I have is the real part, and that is how I map it here. Okay, yeah. So now what about the pole that I have it across my input? Does this input has a pole? At 0 there is a pole, right? Okay, so I will use this mark, okay, the green color for denoting the pole that is coming from the input function. Okay, and the pole that is coming from the transfer function, I will just mark it with the violet color. Clear? Yeah. So I have these two poles, and let us see how does this output would behave. Okay, so I guess you might be knowing the answer for this. What type of output you can expect at this particular point? Huh? Yeah, both the poles are there in my S plane. Okay, so as of now, this particular example will not give you the correct picture. So probably we'll just evaluate this y of t and then see how do we draw the output y of t graph. Clear? Now, can you just tell me what is the value of this y of t for this given function, y of s term? What do we do actually? We use partial fraction method, right? So we can split this into something like a by s and b by s plus a, and then you do partial fraction and you will find something like a equals to 1 and b equals to minus 1. Okay. Once you get this particular values, once you substitute back to this y of s, you end up having something like 1 by s minus 1 by s by s plus a, right? Now, how do I translate this Laplace function into a time domain function? So, what happens when I try to apply an inverse Laplace transform? Okay. So, this term is nothing but it translates as 1, right? And then what happens to this? Yeah, e to the power minus a times t. Okay. So, this is what I would get once I plug in this particular thing. Now, having said that, what happens when I have a time t equal to 0? When I substitute the value of t that is equal to 0 here, what is the output that I can expect out of this y of t? What happens, what is the value of e to the power 0? It's 1. So, 1 minus 1 would end up having a value of 0 itself. So, initially you will have a 0, and after then, as the time goes up, what happens is this, the magnitude of this one will go to a higher value or to a lower value. I am talking about this e to the power of minus something. As you increase the value of t, yeah. So, as the time increases, what happens is that e to the power minus t would generally goes down, okay? And what happens is this particular term or the entire term will go down as time progresses up, okay? And at a particular time, what happens is this whole of this term will go all the way to 0, and you finally achieve an output which we call it as a v final or something, correct? So, now it's clearly there are two components in this particular expression, okay? This particular part is nothing but steady state, yeah, okay? And this particular part is called as clear. So, now clearly you could able to see that. So, at the very beginning of our output, what happens is it is this particular natural response that dominates, but after a while what happens to the natural response? The natural response will die out, right? And in a way, after this you would end up having the dominant term coming out of this steady state response, and that is how the output would react, okay? So, now what happens when you have this pole being shifted towards right? Say for example, I am somehow pushing this particular pole to a larger value of this sigma value in the negative scale, okay? Now, what happens to the response? How do I draw the same graph? So, in this case the slope value, or in the previous case the slope value is this, right? So, now the point is what happens if I move this particular pole towards the left hand side? I think you might be knowing about it. Steeps up or steeps down? Steeps up, okay? So, the answer to this is basically it goes higher and higher. So, as I shift towards larger and larger value, what happens is your output will go with much higher steeps. Is that clear? Yeah. So, later I will tell you like how does this minus a maps to what, okay? So, basically this minus a is nothing but your 3 dB frequency, okay, that you would get. I will talk about it later, but as of now this is what would happen, okay? As the bandwidth of your system keeps on increasing, because as you increase the value of a in the negative axis, what happens is the bandwidth of the system also increases, okay? Now, due to which this step basically has infinite number of frequency, okay? And possibly as the bandwidth of your system is becoming larger and larger, then what would happen is the system is capable of allowing almost infinite number of frequencies, and in a way that this can produce an output which is almost steeper like this, okay? If the bandwidth is so small, then you will have only the low frequency component, and when you try to build that with a kind of response, the low frequency component will have a kind of slowly varying curve, okay? But as the bandwidth of your system is much larger, then you would get a response which is like sudden height in your graph, okay? Is that clear? Yeah. So, now let me talk with respect to some example, okay? So, let me have a system and this time the system not only has a single pole, but I also have a 0 in it. Okay, and let me try to draw those locations in my S plane. So at -2 I have a 0, so which I denoted with a circle. Okay, and again at -5 I have a pole which I label with a cross symbol. Okay, now to this what I am trying to apply is a step input, right? Now this step input has a transfer function which is 1 by s, and this 1 by s will obviously be placed here, okay, as a pole at the origin. Okay, so now I will not do the math. The only thing is I will write down what is the value of y. Okay, so after doing all this partial fraction method, you end up having this expression to be. Now what would be the value of this y of t? Okay, yeah, so we know this 1 by s would turn out to be 1, so I have 2 by 5, so it would be 2 by 5, and we also know that this particular term would translate into, how does it translate? 3 by 5 e to the power minus 5t. Okay, yeah, so now the point is, we are not really worried about the output as of now for the step input, but what I am really worried is which are the terms that are contributing to what. Okay, which are the poles which are contributing to which particular part of my system response. Now when I look, can you tell me which is my natural response and which is my force response in this particular expression? Okay, so this 2 by 5 is nothing but the force response, and this entire term would be my natural response, right? Yeah. Now can you identify which are the components that are contributing to which part of my output y of t? Who is responsible for this natural response? The pole of system or the pole of my input? Okay, so you could be able to clearly see right away, just because of this -5 which happens to be from the pole of my system. Okay, the natural response is basically defined by. Now when I look for a force response, which pole or which part of my S plane is contributing to my force response? Who is contributing to that? The force response is coming from poles of the system or poles from the input or 0 from the system. You could actually look into this particular expression. There is something like 1 by s, right? And that has been multiplied by 2 by 5. So we will not worry about this 2 by 5. But where does this 1 by s has come from? Yeah, it is basically coming from the input pole. So I can straight away say that. Now we'll look for this 2 by 5 and 3 by 5. Okay. Who is responsible for these values? Okay, 0. Is it only 0 or? Okay, so it's a contribution from almost all the people that we have. Okay, so it is both poles as well as zeros. Okay, the magnitude part, which is 2 by 5 or 3 by 5, is basically defined by both the poles and the zeros. Okay, there is nothing like specifically from the poles of the system or specifically from the poles of my input. Clear? So let me summarize these statements. Yeah. So now what we do is, like, we will just look for the step response of a second order system. Okay. Now I'll just take a generic transfer function which is having a second order as its polynomial. And this is my h of s, and I have my x of s and then y of s. Yeah. So now In the previous case, we had a parameter which is named as minus a, right, in the first order system, okay, and that was actually defining our natural response. Okay, now this minus a parameter can be utilized for defining two timing parameters. One is named as the rise time, okay, the other one is basically the settling time. So I will not go much in depth, but basically there was a particular parameter, there was a single parameter out of my first order system that basically helps me to define these two timing parameters. Okay, but when I go for a second order system, there are two type of parameters that are important in this particular case. Okay, so one of the parameter we call it as a natural frequency, okay, which I'll take it as omega n. And what does this natural frequency means? What do you mean by this natural frequency? I think you would have already learned. Yeah, some sort of oscillation will happen at the output, okay, without any damping. Okay, now clearly from here I can just extract this particular thing. So there is no damping, and I can equate this. Okay, so when there is no damping, then this h of s could be evaluated as or written as something like b divided by s square plus b. Okay, because we know that there is a term, and this particular term is responsible for some sort of damping. Okay, later I will talk about one more parameter which is nothing but the damping ratio, but as of now, in order to evaluate this omega n, what I have to do is, like, I have to assume that the system is having no damping, so that the transfer function h of s that I have written at the top would end up having something like b divided by s square plus b. Okay, now from here I could write that the value of this omega n is nothing but the square root of b. Okay, how did I write that? It's straight away from this polynomial. Okay, so I can get a characteristic equation. I can just directly write it as something like this. Okay, so we know that S tends to j omega, you know all of these parts, right? So in that particular way we can evaluate it. Okay, so I'm not going to go much in depth. Okay, so this is my omega n, and that is nothing but the b term that is sitting at the top. Okay, so the next parameter that I want to talk is about the damping ratio. Okay, so where the damping ratio I will denote with the symbol eta, and it is defined as something like so it's nothing but the exponential decaying factor divided by the natural frequency. Now what is this exponential decaying factor? From the first order system response, we had something like a, right? How does this a sits to its output y of t? E to the power minus a times that of t. Okay, so that is nothing but the exponential decaying factor. Okay, so basically the real part, okay, which is nothing but the sigma. So in general, if I look back into this, you could be able to see that this real part of my pole generally appears as a kind of exponential decaying factor over there. Okay, so generally when I talk here, the exponential decaying factor, I am talking about only the real part of my pole, system pole. Okay, and that's the reason why I have taken it as sigma here, and I am going to take the magnitude of it divided by the natural frequency, which is nothing but this omega n. Okay, now so based on this, I can write that the value of the sigma could be written as a by 2 divided by this omega n, and you would get a to be equal to 2 times that of eta divided by omega n. Okay, so I'm not proving anything in these two things. I just want to emphasize that there are two type of parameters, which is nothing but the natural frequency and the damping ratio. Okay. Now with these two parameters, I want to analyze where does this pole will lie, how would be my output for this response for the step input that I have. Okay. Shall we do that? You have any doubt? Yeah. Huh? I think this is something like we generally write it as a kind of a square plus b square plus 2ab, right? So this is the form that they wanted to get down. Okay. So we already know that this b is nothing but this omega n square. Okay. So if I want to have it like this, I can even write this particular transfer function, which is written as h of s equals to something like this. I can write it in terms of this omega n and then the damping factor or the damping ratio. Okay. So how will I translate these two things into h of s? How do I redefine the value of a and b with this omega n and eta? How do I redefine it? How do I rewrite this in terms of not just a and b, but what I wanted is in terms of damping ratio as well as omega n? What do I substitute for the value of b? Omega n square divided by s term will sit as it is. What happens to this a term? Yeah, so that would translate something like 2 times that of damping ratio times that of omega n, plus again I have a b term which translates to omega n square. Okay. So we wanted something like a square plus b square to plus 2ab. Okay. And that is how we get the term 2, and you can actually map these two terms, you would end up having something similar expression. Okay. So we will not go much in depth. The only thing that I want to emphasize here is for a second order system we have two important parameters, which is one is natural frequency, the other one is the damping ratio. Now what happens the moment the damping ratio varies from the value of 0 to all the way to infinity, positive side. Okay. We will see like what would happen to our S plane and our step response at the output for a second order system. That is more important for us conceptually. Okay. But given a response something like this, I am just telling like how to translate this, how to extract these two parameters is what I am showed here. Okay. Yeah. So now how do we evaluate the pole locations based on this second order polynomial that I have written down? How do I extract the pole information from here? Is it so tough to answer it? I think if you have something like this which is equated to 0, then we know something like minus b plus or minus square root of b square minus 4ac divided by 2a. Yeah, so based on this we can compute it. So I just want to know the poles omega or s1 or s2. Okay. We know that the second order polynomial in general will have two poles, correct, or two roots basically. So what are those roots is what I am asking here. So now what happens in this case, the poles or the roots of this particular quadratic equation. Okay, so it would be something like minus zeta omega n plus or minus omega n with, okay, so something like this we would end up having. Okay, yeah. So now based on this roots we can actually plot this S plane. Okay, so what I am going to do is I am just going to vary this particular zeta factor right from the value of 0 to all the way to a much larger positive value, and see how these poles will go around our S plane and what type of response we would get at the output, okay, for a step input. And that is the ultimate aim for us to discuss about this particular topic. Okay. Omega n, okay, here, right? Yeah, yeah. So now let us see like what happens the moment I have this zeta that is equal to 0. Now what type of roots that would appear? Like what happens the moment zeta becomes 0? Okay. Yeah, so the point is, since this particular term goes to 0, I have square root of minus 1. What happens to the square root of minus 1? How do we represent that? As a j factor, right? So I would end up having something like minus j of this omega n. And now how do I plot this in my S plane? So it is something like I have sigma here, and then there is a j omega term here. And how will I plot these two poles of the system? Yeah. So somewhere on my y-axis, whose value is plus j omega n, and somewhere in the negative scale, I would have minus j omega n. Now, how would it respond, or how do I draw the graph of my y of t for a step input x of t? How does it? How does this pole will define an output for me? We know that the poles in general, because from the summary I could say that the poles of the system defines me the natural response. Okay, how does these poles, which are located at the imaginary axis, would appear in my would define my natural response? How does it defines my natural response? Yeah, just a sinusoidal. Okay, and this can it decay first of all? Can this response, natural response, will it decay? Okay, so in a way, what is the value of this sigma here, which is my real part, right? In the expression S equals to something like this. What is the factor of this? What is the value of this particular sigma here when I have poles exactly on the imaginary axis? 0. So now we know that this would actually translate to some kind of exponential term, which is sigma t. Now when this becomes 0, then the entire term goes to a value of 1. Okay, so I know that this natural response will never die out. Even whatever the time it will never die out. So the natural response will stay as it is. But this particular part, which is nothing but the j omega n, will create a kind of sinusoidal signal. Okay, so the output that I would get is some sort of thing. Over a time, I will get a continuous amplitude. Okay, the amplitude is supposed to be constant. I have written wrongly. I have drawn something like growing, but generally the amplitude stays constant, and then it goes something like this. Okay, you will have a sinusoidal output, and there won't be any steady state response for this. Okay, it will never reach, because the steady state response is dominated by the natural response. Clear? Now let us go for the other situation where the zeta value is falling between 0 and 1. I'll just take this, I'll just copy this. So what happens the moment the zeta falls between 0 and 1? Yeah, so we know that the value is always lesser than 1, and due to which I can rewrite this one as something like, pulling out a negative term, I can write it as something like this. And when I pull out this negative term, it appears as something like j, and the whole of this expression could be written as something like this. Okay. Now let us try to plot the S plane, and where does this pole will lie? It has real part, right? So it has a real part sigma value, as well as it also has imaginary part, whose frequency would be omega n times that of square root of 1 minus eta square. Okay. Now how do I plot them? Is the real part is in negative scale or in the positive scale? Is in the negative scale. Okay. So I will have a pole somewhere sitting here. Okay, and one more pole that is sitting here, and the frequency or the imaginary value would be something like plus j omega n times that of square root of zeta square, and it will also intersect with my real axis, whose value is nothing but minus zeta times that of omega n. Okay, so similarly I can write. So I have these two poles. Now how will I represent these two poles basically? So we know that the real part, since I have a real part, I will have some kind of exponential term. Okay, and this exponential term will generally die out. So So will my steady state response after a particular time, will it become dominant, or will I have only the natural response throughout the entire response? Yeah, so yeah, since because of the existence of my real part term in my pole, what happens is the natural response eventually dies out after a particular time, okay, and then the other term, that is nothing but the forced response, will come into dominancy after a while, okay. So let us try to figure out how does it happen by plotting this t with respect to y of t. How do I draw the graph for this? Whatever response I would get. Okay, but I also have some sort of sinusoidal term, because this is my omega term. So there will be a sinusoidal, as well as there will be a kind of decaying factor as well, okay. So for a step input, the response would go something like this, and then after a while it decays, okay. Now the rate at which this decays is basically defined by the sigma term, okay. The rate at which it dies out comes from my sigma term, clear? Now clearly there are certain parameters that we can evaluate, okay. So I can evaluate the rise time, okay, which is nothing but 0.1 to 0.9 percentage of the swing, okay, and there is also something known as peak time. What do we mean by this peak time? Yeah, so what happens is you could be able to see, even though the step input, even though my final output is something like this, you could be able to see that the output response goes beyond the final output, okay. There is some sort of peaking that happens, okay, and the time at which the maximum peaking happens, we call it as a peak time, okay. And we also have a settling time, and there is also known as a peak overshoot. So there are basically 4 parameters that we can take out from this omega n as well as zeta factor, okay. So the natural response, or basically the response of my system would look something like this. And what do we call this response as? Overdamped or underdamped or undamped? What do we call them? There is something known as critical damped, okay. Overdamped or underdamped, yeah, okay. What do we call this response as? The previous one, undamped, okay. So now what happens the moment I have a zeta that is equal to 1? Yeah, so we will have a critically damped position, and what happens to this term when zeta becomes 1? So 1 minus 1 would turn out to be 0, so this entire term goes to 0, and what we have is only a real part, okay, and this real part has 2 poles, okay, sitting one over the other, okay. So and the frequency at which it sits is defined as something like zeta times that of omega n, and since the value of zeta is equal to 1, I can even write this as just omega n itself, okay. And the output response, how I can draw the output response for this type of system where the poles are real and there is no imaginary part? Will there be any oscillations in my output? There is no oscillations, okay. So it is something similar to your response that you would get when you had a single pole in your system, which was an exponentially increasing graph, right? So similar to that, I will have a kind of graph. Now finally, the other thing is, like, what happens the moment you have zeta that is greater than 1, say for example 2. So obviously this term will not be equal to 0 right now, but what I would get is there are 2 type of poles. One would be here, the other one would be here. Both the poles are real, okay, there is no imaginary part. And how do I define this pole location? What is the value of that? Okay, so minus zeta omega n. Should I need to put a plus symbol for this or a minus symbol? Plus, yeah. So plus omega n times that of zeta square minus 1, and for this the only thing is, like, there is a negative sign that I need to substitute here, okay, because it is more negative. Now how would the response would look for this type of system? Will I have a much larger slope when compared to the previous case where zeta is considered to be equal to 1? When I compare to this, how do I draw the slope of this second or this particular system? Underneath or above that? Do you think? Do you think steeper? Which is the dominant pole in my system in this case? The one towards the left or towards origin? Towards the origin is the dominant one. Okay, so due to which, because of this particular guy that is dominant, what happens is the response of the system would be much more slower. Okay, so I just want to finally show you one particular one of the term will die out fast, but the other term that is sitting closer to it, no, it will not. It is moving towards the right origin point. Yeah, I will show you. These are the responses, and you could be able to see that the response of zeta that is equal to 2, it's been plotted in GNU plot. Okay, so as the value of zeta goes all the way from 0 to 2, the response of 2 is basically very lower than the response of zeta equals to 1. We can actually plot it and see. Because the bandwidth of the system is defined by the pole that is located closer to my origin, not the pole that is sitting in between.